Okay, we can start now. So welcome everyone. So Professor Bloch will give his second talk today, and he will talk about quantum simulations using ultracold atoms in optical lattices. So over to Professor Bloch.
Okay, welcome back everybody. I hope you can hear me, see my slides. I want to continue the lecture today where we left off in the last class yesterday. So I just want to remind you again the type of models that we discussed. Well, these Hubbard type model systems where you have atoms with which model the behavior of electrons or other particles in lattices, and they can have two spin flavors, which we denote here by these colors. These can tunnel through the lattice. They can interact on a given lattice side via this on-site interaction. That's all what we want to consider in this lecture. So we're not even talking about long-range interactions here. And we also discussed that when you have a unit filling and you're in the regime of strong repulsive interactions, for example, you can map this model, this Fermi-Hubbard or Bose-Hubbard model becomes an effective Heisenberg model with ferromagnetic or antiferromagnetic exchange couplings for the spins sitting on neighboring sites. I will remember for bosons, we had the ferromagnetic coupling. So this J term would actually be negative here. So it's energetically favored in the ground states if the spins align. They are parallel, and like what you expect from a ferromagnet, that the spins are aligned. And if J is positive, then the energy is minimized when the spins anti-align, and you get basically a Heisenberg antiferromagnet. So this is the big difference between bosons and fermions when you look at two-component spin systems, that you have these very, very different phases of matter. Again, the coupling strength here, how strong is this super exchange coupling between neighboring sites? It's basically given by the second order perturbation theory expression for t squared over u, where t is this hopping matrix element and goes in squared divided by the denominator here, which is the intermediate state energy of the second order perturbation theory process. This gives you the coupling strength. Okay, so now let's connect this to something interesting, which I'm showing you here is a phase diagram of the cuprate high TC superconductors. And these are actually layered systems, so they are 2D systems, and you can have of electrons, and you can have holes, for example, doped in the system. And for zero doping, you are basically exactly in this regime of having one electron per site, 50% spin up, 50% spin down. And if we look at the phase diagram of the system, you see actually below a certain critical temperature or below a certain temperature level here, you see indeed you get this antiferromagnetic ordering, which is precisely this Heisenberg antiferromagnet we've been talking about. So this really occurs in materials, and as we'll see, it also occurs in these cold gases. So now the interesting thing, what people don't understand today, where there's still huge open questions, is what happens when you start to introduce holes into the system. So you're really trying to understand the competition between hole motion, hole doping in the system, and this antiferromagnetic ordering, and try to understand how this gives rise to all these different very, very weird phases of matter. And this is, I think, one of the biggest problems, outstanding problems in solid state physics, to solve the riddle surrounding this, the puzzle surrounding this phase diagram. So essentially what you are trying to do is you're trying to understand, and this is what we will look about in this lecture today, how does this magnetic ordering, like this antiferromagnetic ordering, compete with the hole motion in the system, where holes want to delocalize to minimize their energy. You remember that a single particle will minimize the kinetic energy if it's in a completely delocalized state, a delocalized wave function in the system. And so we're going to look at this competition between hole delocalization and magnetic ordering in the system today. So now we switch over from the bosons we looked at so far to the fermionic model. And we also have this beautiful tool of the quantum gas microscopes available there, where we can see like individual atoms and individual spins, even, as I'll show you in a second, in a spin resolved way. So we can really say where are all these particles in the system. So here's a first experiment that I want to show you from Markus Greiner's group, realizing precisely such antiferromagnetic systems of fermions in this optical lattice. So remember, you have this optical lattice, square optical lattice, You put 50% spin up, 50% spin down, fermions in there. Here in this case, these are lithium-6 atoms, 2 hyperfine states from lithium-6. You make the temperature cold enough such that you would be in this antiferromagnetic phase from this phase diagram. And when you take a photo of the system with this fluorescence imaging that I introduced to you yesterday, you see a picture like this one. So you see in a spin unresolved way, you see where all the atoms are in the system, but you cannot say where is a spin up or a spin down in the system. Now, here's a nice trick that you can apply to see where one of the spin components actually is, how the spin's oriented. You can actually remove one of the spin components. Let's say you remove this spin down component by shooting in a laser beam that pushes out those spin down atoms. And then basically you are left with only the spin up atoms. And now you can actually see beautifully from this picture, what we couldn't see from this picture, that if we only look at the spin up atoms, then we actually see, oh, it's really nicely aligned in this checkerboard pattern that we expect for an antiferromagnetic ordering. So actually, you also know where the spin downs are, because each time there's a hole, a missing atom here, you know that must have been a spin down particle if you're coming from a system where every lattice site was originally filled in the physical system, okay? So this works actually very nice, and you can actually look at correlation functions, G2 correlation functions, spin-spin correlation functions, and you see that indeed, if you are low enough in temperature, you can have antiferromagnetic ordering, which extends over the entire size of the two-dimensional system. Whereas if you go to higher temperatures, if KBT becomes larger than this exchange coupling strength, so remember this coupling strength, which is important here, is this exchange coupling. If temperature is larger than J exchange, we cannot expect the magnetic ordering to occur. If temperature is lower than J exchange, then we enter this antiferromagnetic phase here. So if the temperature is low enough, you can indeed see that you get this beautiful antiferromagnetic ordering in the system. Now, one problem with this detection method is that if you have a lot of holes now, if you would dope the system with holes, if you were to introduce mobile holes into the system, and a lot of them, let's say 20, 30, 40, 50% of holes, then of course, when you take such an image where you remove the spin down component, you do not know whether this missing atom here, is that actually a spin down or is it actually a hole, right? Because it could have been a true hole that was in the system as well. So you don't know that. And therefore, this detection method becomes limited. And we need to look at ways how to do this in a better way to image that. And I'll tell you how that works. Okay, let me first start to show you a little bit what you can do with such images. So let's say this is a single picture from our quantum gas microscope for lithium-6 atoms, for fermionic particles on the lattice. They are not imaged in a spin resolved way, but they are imaged in a density resolved way. So you see the lattice sites here marked by the squares. And each time there's a bright spot, this is a single atom on that lattice site. And you can really see, we can beautifully see each individual atom on these different lattice sites. You can also see sometimes sites where there is double the fluorescence. So this is actually doubly occupied sites where you have two atoms on that image, on that lattice site. So now you can take such an image like this one and make use of the knowledge of your point spread function, for example, of your imaging system, and use a reconstruction algorithm, a computer algorithm, to take such an image, raw data, and convert it into an occupation of the lattice sites. So this would be then what comes out of this single image, where you can tell now whether the lattice site was occupied or not. If it's occupied, we mark this with a blue circle. If there are two atoms on that lattice site, we mark it with a red circle. And from this picture, we can actually beautifully reconstruct the occupation that we had on the lattice. That's a single picture. So now let's see what we can do if we have several hundreds of those. Well, the first thing you can do is, for example, you can just calculate the average density of your system. So you can take 500 of these images. Each one will be slightly different. Remember, it's a different configuration of the many-body state. And then when you average them, you get, of course, then the average local density in the system, which you can see here. But if you have access to the snapshots, you can do more. You can also look at, for example, fluctuations. What is the fluctuations, the on-site fluctuations compared to the average density, for example? Because in each shot, there might be a slightly varying atom number on that side. You will have a fluctuating atom number on the lattice side, allowing you to calculate the variance on that lattice side. And if you compare that to the mean, you can tell something that's known very well in quantum optics, that is the number that is so-called number squeezing. So how much number squeezing do you have? So remember, for a Poissonian system, the standard deviation goes like the square root of the mean. So the variance goes like the mean. So for a system which would just be, you know, shot noise limited with Poissonian statistics, this number would be 1. And now, of course, we can be in states of matter, in insulating states of matter, like this Mott insulator or a band insulator, where you have exactly a fixed number of particles per lattice site without any fluctuations in the particle number. And then this would give you a actually reduced number, with the number squeezing being smaller than 1, and this telling you quantitatively how much reduced those fluctuations are. And you can actually see here very nicely in this picture that here in this region, in this blue part, you have quite low number fluctuations. But in the surrounding, in the boundary of the system, this is where all the fluctuations of the system are actually stored. And then you can actually also do things which are even cooler. You can calculate, for example, the local entropy. If you remember your statistical physics course, the entropy is just defined by the probability of a certain configuration to occur times the logarithm of that probability. And then we have the different on-site occupations that we can have, 0, 1, or 2 atoms that can occur, for example, in the system. And by measuring this occupation, we have access to the probabilities of those configurations, 0, 1, and 2 on each lattice site. And thereby we can calculate how the entropy is distributed in this many-body system in a lattice site resolved way. So we can even look at these local regions here and say, okay, this is a region with very low entropy, and the ring outside here, the perimeter of this gas, actually carries a lot of entropy, carries most of the entropy. So we can really make also use of this statistics to measure how entropy is distributed in this quantum many-body system. And that's very powerful. And now from all these quantities, you can actually, by assuming that the system is in thermal equilibrium, you can calculate things like the chemical potential, the temperature of the system, the compressibility of the system, which would be just the derivative of the mean density versus chemical potential. So all these thermodynamic quantities you can directly access now from images like the ones I showed you. Okay, so let me tell you a little bit how we realize this spin resolved imaging in our lattice systems, how we can not only say where is a single atom or 2 atoms, but we can also say where are the individual spins that we have in that system. Okay, so for that we actually prepared in the first experiments a system where we have a 2D system, but where the spacings in the y direction were twice as large as in the x direction. So the spacing in this direction is twice as large as in this direction. You can directly see that. And these intermediate lattice sites were not occupied, or they were held at a higher potential. And now we can make use of this system to basically now have a spin resolved detection in the following way. We can do the following trick. Let's imagine you have a one-dimensional chain like this one. Let's take 1D chain here, and you want to see now where are the spin ups and downs in the system. So in order to do that, what you do, you take this 1D chain that we have here, and you make each lattice site here, you split into 2 lattice sites. This is done by introducing a lattice potential which has half the wavelength, half the period of the original lattice. So you can basically split each lattice site into 2 lattice sites. So it's like out of a single well, you make a double well. Okay, out of a single lattice site, you make a double well lattice site. And now if you do this splitting process, well, let me actually ask you, if you would just, let's say you take a single atom and you just start with a single harmonic oscillator and you turn that into a double well, where does that single atom end up? See what I mean? You start with a single well, the atom is in the ground state of your harmonic oscillator, you split this now into a double well potential, and you do this adiabatically, and the question is, does the atom end up on the left-hand side, on the right-hand side, or where does it actually end up?
Superposition.
What would you say? Yes, superposition of what? Can we say what the state would look like? Both wells superimposed, that's correct. But how? Yes, any of the two wells, that's correct. But can we say something about which superposition state? Remember, if we have the left wave function and the right wave function of the double well, then we can form any linear combination of the two. But let's say we just want the one with plus and minus sign. Which one is it going to be, the plus one or the minus one?
So according to the adiabatic theorem, it should be the new ground state.
Sorry? Can you repeat?
According to the adiabatic theorem, it should be the new ground state.
Yes, and what is the new ground state? That's correct. What is the ground state of the double well?
I think it should be plus one.
The
Symmetric.
symmetric,
Yes.
symmetric or antisymmetric superposition? So in the double well, you have the two states, which can be psi left plus psi right, or psi left minus psi right. Which one is it going to be?
Should be the symmetric.
Yes, it's the symmetric one, right? Correct. It's the symmetric superposition that you get. You would be delocalized. So when would you end up actually in the antisymmetric? Is there a way you could see how you end up in the antisymmetric superposition? What would you have to do if you have a single atom on this single side? How do you end up in the antisymmetric superposition?
If the splitting is fast enough, then
we want to do things adiabatic. So we want
adiabatic,
to
okay.
state to the other one. So from which quantum state do I have to start in the single well to end up in the antisymmetric state in the double well? What would you say? So basically, we're trying to find out how are the states in the double well connected to the states in the single well. Anybody have an idea? If you look at the wave function, we have, let's say we want the state I'm asking about, the antisymmetric one is psi left minus psi right. Which wave function is that connected to in my single well? First excited state, excellent, very good. That's the first excited state, because remember, that's also, it needs to be an antisymmetric state, right? It cannot be a symmetric state from parity arguments. And the lowest energy state that we have that is antisymmetric is the first excited state in the harmonic oscillator. If you remember your Hermite polynomials, the ground state is the Gaussian, and the first excited state is this wave function, which is antisymmetric. So that's precisely the one that you merge to if you would be in that excited state. Okay, but now we want to do even a little bit differently. Now I want to do the same splitting. We start in the ground state of the single well, and now I want to do the splitting, but I want to add a gradient. I want to split now from a single well into a tilted double well. So imagine you have the double well, and now the double well does not have equal energies on left and right side, but it's tilted like this. So where do you end up if you split into a tilted well? You start out with a single well, and now you go into a tilted double well with large tilt. Where do you end up with your atom? Does it come to the left side, to the right side, or does it go to the superposition, symmetric superposition state again? What would you say? So you start in the ground state here, and you go to this very tilted configuration where one well is much deeper than the other well, much lower in energy. Yes, so indeed, if the tilt is large and you do it slowly, you end up, of course, in the deeper well. Because if this well is much deeper than this one, then the ground state of this tilted double well will just, of course, be the lower energy state of the tilted double well. And then if you just do everything very slowly, again, you stay in the ground state, adiabatic theorem, then you just end up in the lower well, in the right well. Perfect, very good, you understood that. So now we can do this tilting. What is a tilted double well? Well, tilting a double well, it just means you have to apply a potential gradient. If you apply on top of the symmetric double well, you apply a gradient, you tilt the double well, right? You end up with this tilted double well. And now we can apply this gradient by applying a magnetic field gradient to the atoms. And because the atoms have different magnetic moments, this potential gradient will point in one direction for the spin down particles and in the other direction for the spin up particles. So for the spin down particles, let's say the right well will be the lower well, and for the spin up particles, the left well will be the lower well. And if you then do the adiabatic splitting, as I show you here, then the following is going to happen, that the spin down particles are going to go into the lower lattice side of the double well, and the spin up particles are going to go into the upper lattice side of the double well of the corresponding tilted double well, right? And this is how we can separate spin ups from spin downs into spatially two disconnected 1D chains. And now if we take a photo of these two chains, of these two independent chains, then I can get the occupation of this upper chain and the occupation of this lower chain. But because of the splitting process, I actually absolutely know that the upper chain was only occupied by spin up particles and the lower chain was only occupied by spin down particles, right? And then I know the original occupation of my 1D chain because I just have to sum these occupations up and then I know what I had originally. So let me show you how this works. So this is the 1D chain, the original system, for example. And then we do this for a different 1D system because, once you remember, once it's photographed, it's destroyed. We cannot use it again. So we have to recreate psi again. So once we create this state again or another one, we can do the splitting process. And now we split this one line into two lines. And I know that the lower lines, those are the spin down atoms, and the upper line are the spin up atoms. And now I can directly read out from the picture what the original occupation of the original 1D physical system was. So for example, let's go through this slowly. This is the first site. It has been split into double wells, so it has two sites now for detection only. And originally, this was one site. And now you see there's no atom in the upper chain, no atom in the lower well. So this was no atom on the original physical lattice site. So no atom on the first site, mark it. No atom on the second site, mark it. Then we have a spin down particle, followed by a spin up particle, followed by a spin down particle, followed by a spin up particle, two spin down particles, one spin up particle here. And here on the last side, we actually had a double occupancy. We had a spin up and a spin down particle on the same lattice side. So this is how you can see how you can actually reconstruct by doing this actually what we call a controlled Stern-Gala experiment. You remember the very famous Stern-Gala experiment on atomic beams. What you're doing here is exactly a Stern-Gala separation experiment in a very, very controlled way in this double well, where you basically split the single well into a double well, one mode into two modes under the action of a magnetic gradient field, which splits the spins into different positions in space. And that's very powerful now. So now you can take these spin resolved images. Okay, any questions to this detection method that I show you here? So you have
can I add something?
Yes, please.
Okay, in the spin unresolved picture, it seems that in the second entry of the first row, you have something, but then in the spin resolved, then when you do the double well, there's nothing. So why does this happen?
Yeah, because this image, what you see here is not this chain. Remember, when we take the photo, the system is destroyed and we cannot split it anymore. So what was done, a new chain was prepared. Okay, a new chain. This chain is not this corresponding physical chain here. Okay, so just think of this, the physical chain underlying this split chain for detection that you see here is just the one that you see here. Okay, so this is just an example of showing you a image where we were not able to do the spin resolution, or we didn't do the splitting, but it's a different realization. Remember, each time we make a photo, it's a random picture that we get. Okay, because of the random configurations that underlie the many-body state. Was that clear?
Yes, thank you.
All right. So here I show you this chart. This is now powerful. We can see this 2D picture now. We have a charge unresolved system or density unresolved system. And now if we do the splitting, we suddenly get pictures like this one, where we can suddenly see where each of the spins, spin ups and downs is actually present in the system. Okay, I want to show you a new method how we do that. Since you understood the 1D chain method, I want to show you a bit superior method, which we used recently to do similar kind of things in two-dimensional systems. The disadvantage of the method I show you here is that we always need this larger spacing in the y direction to squeeze in the atoms here for detection in this direction. And we don't like that. We want the separation of the atoms to be as close as possible to each other. Do you have an idea why we want that in the experiment? Why do we want the atoms, the lattice spacings, to be as small as possible? Is there anybody who knows why we would want the lattice scales to be as short as possible? Any idea? What does that mean for the tunneling coupling, for the tunneling energy, this T parameter or J parameter that I showed you? How does that change if I make the lattice shorter spaced? How does the tunneling matrix or the tunneling coupling change when you make this spacing between the two wells shorter? Does it become larger, smaller, stay the same?
Larger tunneling.
Yeah, so it will become larger, the tunnel coupling will become larger, and that's of course what we want. We want the energy scales to be as large as possible, so we don't have to cool the system so much to see this interesting many-body phenomena. Because remember, the temperature has to be lower than this hopping or exchange energy scales to see that. So we want to drive those energy scales as high as possible. And of course, if now we have to introduce twice the spacing in this direction here in order to squeeze a line in between, then we actually don't want to do that, because that will reduce the energy scale in this direction a lot, because the wells are now separated quite a lot from each other. So I see there are a lot of questions now. Should we go through them? And, yes.
There is a question from Sourav. Sourav, why don't you ask directly?
Hi. So from shot to shot, how stable are these lattices? I mean, the grids that you have drawn, are they stable from shot to shot?
Yes, they are quite stable from shot to shot. On a hour scale, hour time scale, they can drift a little bit. Why do they drift? Remember how we make them. We make them by interfering two laser beams, right?
Yes.
So anything that changes in the beam path, for example, a mirror that moves a bit mechanically, or your thermal expansion, the temperature changes a bit in the lab, so things change, then of course that will change the relative phase of those two beams interfering, and that will change the position of the lattice. So we have a very good temperature stabilization in the lab to try to minimize such fluctuations. So that will lead to a very slow drift of the underlying lattice. It will stay a square lattice, it will just move in position.
Okay.
The good thing is that, you know, when we see single atoms like this one, we can always, from a single shot, we can tell where the lattice was, what the phase of the lattice was. So we can use a few of these individual atoms that we detect to know where the phase is and predict where the phase is going to be in the next shot, for example, for the experiment. Because we know the drift is slow, we know that from one shot to the next, it will be the same stable lattice, but maybe over 6 hours, it will move. So, but we can keep track, by knowing the position of the atoms, we can keep track of this phase drift of the lattice, and we can correct for it. For example, this is very important. You raise an important point. When you want to address a certain lattice site with a laser beam, want to focus a laser beam onto a certain site, you need to know where to shoot the laser beam, right? You need to know where the lattice site is. So this is a very important question you ask. Very good.
Okay, thank you very much.
Any more questions?
There is one from Mrinal Kanti Giri. At
Yes.
empty site, there is also some finite probability in spin result pictures. Why this happen?
Yes, so there's a little bit tricky thing I didn't really explain exactly. So you're probably meaning, well, first of all, there's a little bit, of course, the image of a single atom, you know, is well, let me ask like this. What determines the size of this blob, of this individual blob that represents a single atom, the fluorescence spot of a single atom? What determines the size of this blob actually? What would you say? I mean, an atom, you know, what's the size of an atom? That's 10 to minus 10 meters, right? An angstrom. So we're not see this blob is much bigger than an angstrom. We are talking here about separations between lattice sites of micrometer scale. So what determines the size of this blob that I'm seeing there? What would you say? No, it's not the interaction cross-section. It would even happen for non-interacting particles. So this atom here is totally isolated. It's not interacting with anything, right? It's totally
Diffraction limit.
I think de Broglie wavelength.
Diffraction limit. Diffraction limited.
Of what? Yes, diffraction limit, correct. Of what?
Of matter waves.
No, not of the matter wave.
Light, of the light.
Yes, yes.
Or the detection.
Yes, it's just, of course, remember, it's our objective. We have our detection objective, and that has a finite resolution. So it has a certain aperture, it has a diffraction, it has an Airy function, right? As the point spread function. This is what it is, basically. So this optical lens produces a delta function spike in the image plane, gives us, in the object plane is transferred to a point spread function to a broadened blob in the image plane because of this finite resolution of the system. So what we see here is just the resolution of the objective. So of course, in the resolution of the objective, it becomes on the order of the lattice spacing, a little bit of overlap. We have a little bit of spreading into the different sides. There's another thing that happens here that I'm sweeping a little bit under rug, that we actually have an even finer lattice underlying this physical lattice to do the detection, but I don't want to go into this. So there's a reason why these positions are slightly not centered, that the center of mass of these point spread functions is not always centered on the physical lattice sites, and there's a reason for that, but I don't want to tell you right now. It complicates things too unnecessarily, okay? All right, good. So let me tell you another way how we do this, which is pretty cool. We do a better way to keep the lattice separations short in this 2D regime. So this is, imagine you have this configuration of spin ups and downs, double-ons, hole in the system, and we want to detect it. So an even better way of doing that is the following trick. We separate the planes, again, the spin ups and downs, but we do it with the whole plane. So I take the whole plane and take the spin up atoms and move them into the upper plane, and the spin down atoms and move them into the lower plane of the system. And then if I'm able to do that, and I'll show you in a second how we do that, how that works. If we're able to do that, then you can just take your lens, focus onto the lower plane, take a fluorescence image of the lower plane, then you move the lens, have the upper plane in focus and take a photo of the upper plane of the same physical system, and then you have two images of the spin ups and the spin downs, and you reconstruct the original image in your system again. Okay, so how does that work? So it is a bit tricky, but it underlies some interesting physics, so I want to tell you how this actually works. So imagine this is our single lattice site that we have, and this axis is the z-axis in which we want to split. So imagine you have spin ups and downs on this single lattice site, and you want to separate them. Well, to separate them, we just learned in the 1D system, I can apply a magnetic gradient field, convert this into a double well. The spin down will go to the left side, the spin up will go to the right side. This is the same trick we used in the lines, but now we're just doing it in the vertical direction, okay? Now the separation here is just going to be the separation between these double wells, and unfortunately this separation is not large enough to already image the two planes independently because they're just too close to each other, okay? So because, why would that matter? Because remember, our optical imaging system has a lateral resolution of the order of lambda, but when you have a lateral resolution on the order of lambda, this also means you have a depth of focus, which is also on the order of lambda. So this thing, this upper thing will not be out of focus, this second plane, and you will see them both on top of each other, and you don't want that. So we have to separate them more. How can we separate them more? And you can separate them more by a process so-called topological charge pumping, where you time modulate the potentials. So we time modulate these optical potentials in the following way. And in that way, you can actually increase, in a controlled way, increase the separation between the layers. So each time what's happening, if you're familiar to this, let me explain it in a simple way. What's happening here is basically a Landau-Zener sweep in a double well. So imagine you have your double well here. Wait, let me stop this animation here. Let's say you are here in this configuration, okay? And you want to transfer the atoms to this well. So, and you have a coupling between the two wells, which is given by the tunnel coupling. But now they are off resonant because there's a detuning delta between those two modes, like in a two-level system. Okay. So now if you sweep with your laser in a two-level system, you sweep through resonance, you can adiabatically transfer all the population from one state to the next. So now we do the same thing. We just decrease the detuning. You see here how the detuning changes, how population is now transferred from one well to the next. Okay. And then you do the same thing again. Transfer again, adiabatic sweep again, and like that, you can actually increase the separation between the two planes in a very, very controlled way. And this works really great. So here are some images looking on the side of the atomic plane. So we're taking a side view onto the plane. You're seeing one plane. And then we do this pumping process, and you see how these two spin states are now more and more split in space. And now we can take two images nicely because now the separation is about 30 micrometer. And when we take a photo of the lower plane, the upper plane is totally out of focus and we won't see it, and it will not disturb the image of one of the planes. So this is how this looks. You start with one monolayer, the physical system. You first do the spin splitting, and then you do the charge pumping to increase the separation, and then you take a photo. This is the photo of the spin up atoms. This is the photo of the spin down atoms. And then you can actually take those two photos, just put them together, and you get the original occupation of the 2D system. Okay, so now I know really in a fully spin and density resolved way, I can see where all the spin ups and downs were, where there were doubly occupied sites, where there were holes. So I get a full spin and density resolved image of my system. Okay, so this is now extremely powerful because we want to know how, for example, holes influence the magnetic ordering in the system. Remember, that was our original question, but now such images, as I'll show you now next, will allow us to do that. Okay, I see there's a question here. Will there not be nearest neighbor hopping when this is done? Yes, so this is what we have to avoid. We absolutely have to avoid that during detection, an atom that was originally on one side moves to the neighboring side. So what we do in the XY plane to avoid that is only for detection, we make the XY lattices very deep so the atoms cannot move anymore in the XY plane. Remember, the tunnel coupling laterally changes exponentially with depth. So the deeper you make the lattice, exponentially lower your tunnel coupling becomes, and eventually it becomes zero. So when you make the lattices very deep, you will suppress hopping in the XY plane, which we do for detection actually. So this is a good question. We really need to ensure that during detection, the atoms do not move, that the physics, so that the image I show you here is really a faithful image of what has been going on in this monolayer of the system. Okay, and this is what, of course, we did do a lot of checks to ensure that that's indeed the case. All right, any more questions to this detection method of seeing this fully spin and density resolved images in our lattices for our Fermi gases?
So both images were taken in the single shot. How? I mean, two laser shots were given one after the other, or how were the images?
There's one physical system. Okay, we do the splitting. So now we have two planes, one occupied by the spin ups and one occupied by the spin downs. And then we can first take a photo of the lower plane, and the upper plane is still there. It's filled with atoms, the ones that we had there originally, right? And then we just move the lens and take a photo of the upper plane.
The first flash of light does not change the state of the, let's say you're taking the image for the top layer.
Yeah.
To shine some light, does it not change anything?
Yes, we have to ensure that it does not change the occupation of the upper layer. Indeed. Okay. Yes. That's absolutely crucial, that when you make these images, you do not disturb the other plane, basically. Absolutely. But that can actually be ensured. Okay, and just a check showing you again these two-dimensional antiferromagnetic correlations. When we saw that, we were quite happy because it showed us we indeed have quite nice antiferromagnetic correlations, and we see them in the detection, so we know the detection works well. Okay, I see some questions more. What are the numbers under splitting and charge pumping? Yes, so this was just the separations that we start out with. So originally, The original separation here in this direction was only 1 or 2 micrometer, but then when we do the charge pumping, we can separate the planes over large distances over 27 micrometers. And that's much larger than the wavelength of light that we use to image here. So that's much larger than the depth of focus of the imaging system. So again, the important point is if I now focus the lens on this plane, the other one will be completely out of focus. And this is what you see. Look at this picture. This is the upper plane in focus. The blue atoms are still there. They're also fluorescing, but they're totally out of focus. You cannot even see them on this picture because they're out of focus. So we have to move the lens to be in focus with the lower plane, and then we see the lower atoms and the upper plane out of focus. But in order for to have a good separation between in focus and out of focus, you have to separate the planes over a distance which is much larger than the depth of focus of your imaging system. Yes, and these separations were only in the vertical plane. That's correct. Okay.
I have a question.
Yes.
So this is spin sensitive measurement.
Yes.
So do you use polarized light?
No, no polarized light. The whole, it's all unpolarized light. You see the whole spin sensitivity only comes in this step here, in this second step. Let me show you again. In this step, this is where the spin sensitive part happens. In the first step where we split a single well into a double well. And why is it spin sensitive? Because we're applying a magnetic gradient during the splitting. And a magnetic gradient, remember the 2 atoms have, in the 2 spin states, have opposite magnetic moments. So the forces they will experience are opposite. So one is pulled to the right well and the other spin is pulled to the left well. That's where the spin sensitivity comes from. Okay, it's only from this magnetic gradient field that we apply. All right, any more questions, comments? Discuss? Okay, all right, so now you know our detection process. So now we're ready to do some physics with this. And this is the first thing I want to show you that we actually did last year. It's actually an interesting experiment where you try to do the impossible for a free space elementary particle. So imagine you have an electron here, and the electron, has 2 quantum numbers, the charge quantum number, and it carries a spin quantum number. Now in free space, you cannot separate the electron into 2 objects which only carry the charge or the spin. But I'll show you actually in a solid state system, you can do that. You can inject an electron into the solid state system or remove an electron from the solid state system and create 2 so-called quasi-particles in the system, which carry independently the charge and spin quantum numbers in the system, and which actually then can completely separate from each other in the system. Okay, so let me show you how that works. All right, so let's take this 1D chain, Heisenberg antiferromagnet. In the system, you have this up, down, up, down, up, down, up, down ordering. And let's do the following dynamical experiment. Let's take our laser beam and focus it, shoot it onto one side to push out one of the atoms here. It's like removing suddenly an electron from the system. So then, after you remove that atom from that side, you will have a hole here. And the system will dynamically evolve because now you're not in the ground state anymore of the system. So now this hole will start to move, and you see what this hole is doing. It will just, for example, tunnel. For example, how does the hole move? Well, the hole moves by this particle. If this particle tunnels, this is an empty site, right? So this particle can now tunnel into this empty site. Remember, we are still in the regime of strong repulsive interactions, so we cannot put atoms on top of each other. But if there's an empty site, there's nothing preventing this atom moving over here. If this atom moved over here, it's like the hole has moved to the right. So now this atom can move over here and the hole has moved another space. And then basically this atom can move over here, this atom can move over here, this atom can move over here. So you see that actually this hole now starts to move, it delocalizes in our system. But if you look a little bit careful, there's another object that has been created. There's another object that has been created that are these 2 parallel spins in this process, which I just sketched. There's another thing we created, and this other thing we created is actually the other quasi-particle. This is one of the quasi-particles. We call it a charge on or a hole on here. This is what this quasi-particle is called. It carries actually the quantum number of charge in a charge system of plus E. And this here, this object on the other side that we've created is called a spinon. This is the other elementary particle which actually carries the spin quantum number. So remember, we had originally a electron here in the chain, or an atom, which carried spin and charge. We removed that particle, and suddenly we get the hole, which moves in one direction. And the other direction, we get another quasi-particle, this spinon, which carries the spin quantum number. And if you draw this cartoon a bit further, you will see that this spinon and holon, they can move, they can separate over arbitrary distances from each other. So they become spinon, the spin quantum number, and the charge quantum number in this 1D setting have become deconfined. They can separate from each other, and you've done basically what seemed impossible for an electron in free space, where you cannot separate, the spin from the charge of the electron. In a condensed matter SAS system, you can actually do that, and this is how this process actually works. Now, there's one characteristic feature of this spinon and holon is that both of them actually propagate with quite different velocities. So let's estimate this. What would you say is the velocity with which this hole moves? So how fast does this hole move, or what would be, on what parameter in our underlying model, in the Hubbard model, will the velocity of this hole depend? What would you say? What determines the velocity of how fast this hole moves? And the tunneling strength, very good. Indeed, the tunneling strength will determine that. Remember, the time scale for hopping from one side to the next is given by h bar over t. So basically, the larger my tunnel coupling is, the faster the hole will move, or these particles will tunnel in here, or the hole will move. So indeed, so the hole will move at a velocity which is given by the tunneling strength. Now, what about this spinon object here? What do you think could be the time scale at which this spin object moves? So what will happen? How could this spin object move? The spinon could move, for example, by these two spins exchanging position. So this green spin moves over here, the red spin moves over here. Then you have the two green spins here, and it looks like the spinon has moved from here to here. What?
The interaction parameter.
Sorry?
The interaction parameter J.
The interaction, the exchange energy scale J exchange. This 4t squared over u strength, exactly. That's what determines the velocity of this particle. And both of them are, so one goes with t, the other one goes with t squared over u. So they should be related to each other by t over u, which is just a factor between them. So one is fast, the charge velocity, and one is slower by a factor t over u, which is the spinon velocity here. And we can measure that. How do we measure that? So let me show you the experimental data. So this is the lattice position in our optical lattice of the 1D system. This is evolution time on the vertical axis. And now in terms of tunneling times. And now I basically, at time t equals 0, I shoot out one atom on this side. So you see the hole density is 1 on this side. So you start with the localized hole. And now you see actually how the hole starts to spread. And you start to actually see what we already recovered yesterday in the lecture. You just see what the probability distribution of the hole is after some evolution time. That's just a quantum walk of a single particle. Because the hole just behaves like a single particle that we would put in the lattice. After some evolution time, we get the probability distribution of a quantum walk. And this is precisely what you see here. You can determine the velocity of the walker by just looking at the cone here, how fast the width of this distribution changes over time. Now for the spinon, we can actually also measure its spin velocity. That for the spinon, we can also look at create this up arrangement right next to each other at time t equals 0. And we can look how the next neighbor spin correlations here evolve in time. And we can also see how they spread in time. There's a little bit less structure in there because the temperature is a bit higher in the spin sector. So we don't see the coherent feature, but we still see this kind of cone spreading out. And from that, we can determine the propagation velocity. Yes, so there's a good question. Why is the hole density 0.7? That's just an experimental imperfection. So basically, we were not able to, with 100% probability, shoot out a hole in every run of the experiment. Okay, but we're pretty, and you also see its experiment also a bit imperfect, because ideally we would have only liked to shoot out a hole here at the central site, but you see it always also has a little bit of probability also of having created the hole on adjacent sites. So these are some experimental imperfections that we have in the experiment. All right, so now we look at the data. We take the width of those two distributions, plot them as a function of time, and you see actually for the holes, they have this very fast spreading. For the spin-on, for the spins, you see this very much slower spreading, and you can directly measure these two spreading velocities in the system. And indeed, if you calculate the ratio of both of them, you indeed find that the ratio is precisely this T over U ratio that we would have expected from the theory of the super exchange interactions. Okay, I want to show you now a more interesting correlation function, and which brings us to these higher order correlators, which are interesting to characterize processes like this spin charge fractionalization of the electron in a much better way. And the correlator I'm looking out for now, the correlation function, is the following one, where I am asking the following question: how does the spin environment around holes look like? So how is the spin on site I-1, this site here, correlated with the spin on site I+1 over here, okay, conditioned on having a hole in between? So this is what this correlator measures, what it tells us on this correlation function. So you're evaluating how does the spin environment look like surrounding a hole. And then, of course, you can calculate the expectation value of that. Now, let's take this chain here and look what this looks like at time t equals 0. At time t equals 0, when I kick out the particle here, I will have a hole here, and the spin environment around the hole will be ferromagnetically aligned. So the spin here and the spin here will be aligned. So this correlation function at time t equals 0 will be larger than 0, will be positive, because these two spins adjacent to a hole at time t equals 0, when I kicked out the particle, will be positive. Now, when time goes on and the system evolves, remember the hole is moved in one direction and the spin-on is moved in another direction. And then actually, if you look at the correlation function of this spin-hole spin correlator, again, which measures the spin correlations around holes, you actually find that in this case, now at later times, the hole has antiferromagnetic correlations surrounding it, because the spin-on actually has moved in the other direction. So the spin-on that was originally attached to the hole at time t equals 0, when we removed that particle, has moved away. So that spin 1/2 degree of freedom has moved away, and you're left here only with these antiferromagnetic correlations around the hole. And this is a direct measurement of the fractionalization of the spin and charge of the particle that we removed from the system, actually. So here's how this looks like in the data. So we're plotting this spin-hole spin correlator, just looking at these thousands of snapshots from our system after kicking out a single atom at time t equals 0. And we see it starts out positive. And then as time goes on, you see how this goes negative and then settles onto the background value of this antiferromagnetic correlation around the hole. And the other spin-on has moved away from this hole. So you can directly see this fractionalization process in this 3-point correlation function. Okay, I want to actually show you how this dynamical feature, what we call spin charge separation, you understand, I think now why it's called spin charge separation, because we removed this particle and the spin degree of freedom separated from the charge, or in our case, density degree of freedom. So this is why this process is actually called spin charge separation in condensed matter physics. So what I want to show you now is actually a very intriguing connection to the ground state physics of the system that directly reflects this dynamical behavior that we got when we kicked out one of the particles. So I want to look at the 1D case, and I want to basically now ask, what is the ground state of a 1D Heisenberg chain, antiferromagnetic Heisenberg chain, when I put holes into this chain? Okay, how does the ground state of the 1D antiferromagnetic system looks like? And there, to answer that question, you again have to think about the two things that minimize energy. So for holes, remember, they minimize kinetic energy by delocalizing. Spins, on the other hand, in this antiferromagnetic Heisenberg model, minimize magnetic energy by aligning antiferromagnetically. Okay, so if I look at the ground state of a, let's say, 1D chain with a hole and ask what is the lowest energy many-body state that I can have, then it would be of the following structure, where you have antiferromagnetic alignment of the spins, and the hole being in a superposition, being everywhere on the chain. It's completely delocalized, the hole. This is where you minimize the kinetic energy. Just like plane waves in free space for a particle minimize kinetic energy, these extended waves in the lattice, these Bloch waves minimize the kinetic energy of our hole also. So it's in the superposition of being everywhere. But note that in the ground state of this system, it's actually favorable to have antiferromagnetic alignment around holes. Why is that? Well, imagine that this particle moves in here, over here, then of course it would be much more favorable for this particle to be oppositely aligned to this one to minimize magnetic energy cost, okay? So this is the ground state of the system. This would be the first excited state, for example, but this is how the ground state of that system actually looks like. So to picture that a little bit better, to understand a little bit better, this is actually quite a remarkable thing, because what this single hole does, is to affect not only the vicinity of the hole, but it really affects the entire system. So let me show you what I mean by that. Let's imagine we start out over here to the left of the hole with an alignment down, up, down, up, down, up, down, up. Okay, so this type of alignment, and then comes a hole. Okay, if the hole would not be there, I would continue here with down, up, down, up, down, up. But now I have a hole here, and we know in the ground state of the system, the hole wants these two adjacent spins to antiferromagnetically align. So I go on here, actually not with up, down, up, down, up, down, but I continue with down, up, down, up, down, up. And if I denote these two configurations of the antiferromagnet that I can have by their parity of plus and minus one parity, then you actually see that a single hole is like a domain wall, introduces like a domain wall for the parity of the antiferromagnet to the left or to the right hand side of this domain wall. Okay, so you get a parity flip in the antiferromagnetic ordering. And what's also interesting about this hole is that this individual hole actually is a so-called topological excitation. What do we mean by topological excitation? Typically, if we make a hole in a 3D system or an impurity in a 3D system, it only very locally affects the environment of the system. In 1D here, this is very strange, because this one hole here not only affects what happens in the immediate vicinity of this, but affects the spin thousands of lattice sites away of it by imposing this ordering of the antiferromagnetic system, right? So this single hole has a very, very non-local effect on the entire many-body system, and that's why we call it a non-local topological excitation, because it has this effect on the entire state of the many-body system. All right, let's okay, so there's a question actually, to which direction will the hole move? Yes, that's, I just moved, you are completely right. Well, you can answer, try to answer yourself. Let's say we would kick out, you're in the dynamical experiment again. So imagine we remove a particle and we have a hole here, to which direction will it move to? Very good question. So what would you say? Which direction will the hole move to? Think of it as a particle. Think of it as a localized particle in an empty lattice. Which direction is it going to move to? What would you say? A few more guesses. There's somebody already wrote in the chat. Let's see more ideas. Lower energy. Yes, it will lower its energy by delocalizing, but in which direction? It's not going to, diffusion is not right. It will not diffuse. It's a ballistic propagation. Actually, you can, that's a good question actually, with the diffusion. Look at how the hole spreads, the width of the probability distribution of the hole spreads linearly in time. So it's not diffusion. What would it have to be for diffusion? If it would be diffusion, what would be the width of the probability distribution as a function of time? If it would be diffusion. So how is the width of the probability distribution? of the particle connected to time if for a diffusive process or a ballistic process? What are the differences? Yeah, just go ahead. You can just unmute yourself, chat, whatever channel you want to use, you can use. For ballistic, we saw here it's linear in time. But what is it for diffusion? Ah, it's very good. Square root of t. Perfect. Thank you, Suman. So square root of time for diffusion process, random walk process, but for ballistic process, this is linear in time. So it's not diffusion. It's just ballistic propagation. And ballistic propagation is just like a single particle on a lattice. And remember, that's just our quantum walk. And if you ask me, does it go to the left or to the right? Well, it goes in both directions, right? The wave function spreads out symmetrically to the left and to the right. And only when we make a measurement, we will find the particle somewhere in this region where the probability distribution is non-zero, right? So we cannot even say whether the particle moves left or right. It actually moves in a superposition left and right. And when I draw these sketches like the one here, you should always keep in mind, when I draw a sketch like this is just one possibility of how the atom could have moved. Just one configuration, one cartoon configuration. It could have moved in the other direction. Actually, in this process from here, it can not only propagate further, it can of course also propagate back, right? So this particle can move in here, and then the whole would have moved back. So we're back to this quantum walk, where the particle in each point in time, it can move to the left or to the right. And the result of this quantum walk is this quantum walk probability distribution. And this is what I showed you here, what you actually also recover for the whole. This is why the whole probability distribution after some evolution time looks exactly like the probability distribution of a single particle on an empty lattice. Remember that from the last class? Maybe I try to go back to that probability distribution.
So if it suddenly goes towards the opposite direction, then the spin-on will destroy.
Yes, that's true. That's true, because we also have to have momentum conservation. And but not necessarily, but there's always the quantum fluctuations in the system, the quantum uncertainties that we can have on top of that. So it's not that simple. So remember, this was the probability distribution for a single particle on a lattice. And for longer times, it looked like this. And what we get for the whole is exactly the same thing. So I have to go fast forward again. Sorry, it takes me. Let me jump out of this for a second. One moment, I'll be back to jump to the right point of the talk again. Okay, let me share this window again. Okay, so now you should see that again. Get my chat window again. One moment. Okay, here you go. So so yes, you cannot even say whether it moves left or right. It moves in both directions, essentially. Yes. So these are just, of course, keep in mind, these are just cartoon pictures of what's going on in the system. But now we're not, actually remember, now the whole is not moving at all. We're not talking about dynamical evolution of the system. We're talking about the ground state of the system, which we introduced holes into. So think of the ground state of the system as something like this. This is the object we're dealing with now. Then nothing is moving here. The whole is, nothing is moving anymore, right? So what I'm now just to explain the phenomena to you, I'm just typically focusing on one of the configurations underlying this many body state psi to explain the physics, what's going on. But of course, they're equivalent configurations, and the actual state of the system is a superposition of these configurations. But yeah, so you're getting at important points. You're seeing that the explanation is more complex, but I'm trying to keep it as simple as I can for you to understand the data. Yeah, so there's another good question. Why the spin-on data does not show interference, only a single peak? Yes, a very good question. This is because the temperature in our system is not low enough to see this interference structure. So remember, somebody yesterday asked what happens to this interference structure if you couple it to a bath, to a thermal bath. Then I told you that interference structure would go away. And in heat here, something similar happens if the temperature is larger than this exchange energy. Then, or in the order of the exchange energy, then this nice interference structure is washed out. Okay, so the temperature is in a regime where it's much smaller than the tunneling, because there we saw the nice interference pattern, but it's on the order of the, or only slightly less than the exchange energy scale. So there, these interference structures are a little bit washed out. Very good question. Okay, but now let's go back to the ground state and let's try to understand how this dynamical spin charge separation occurs in the ground state. And let me show you the data of this really happening in the system. So here I'm now plotting this. Let me walk you slowly through the data. So I'm plotting this spin hole spin correlator again now. So we're asking again, how is the spin on side I correlated with the spin on side I plus D? Okay, this is a spin-spin correlator. How are these two spins correlated? Conditioned on having a hole at site S. Now there are two possibilities this S can take. So the hole can be outside of the two spins we're correlating. So S can be larger than D. That would be this configuration. So if the hole is outside of the two spins. And then of course I would just see my standard antiferromagnetic ordering up, down, up, down, up, down in my correlation function of these two spins. Or the hole is between the two spins, then it's over here. Then actually you see that you remember that each time you crossed one of those holes, the parity of your antiferromagnetic ordering is flipped. So the antiferromagnetic correlations should also have flipped in this 3-point correlator. And this is what you see here. So this is the distance of the two spins we're correlating, D. Distance where the hole is. If S is smaller than D, then we're in this sector here. Then we're in this situation. If S is larger than D, then we're in this situation, and we have in this configuration here. Now let's go to this configuration first, and you see actually if the hole is outside of the two spins we're correlating, then we have this nice down, up, down, up, down, up, down, up antiferromagnetic correlator. But now you see if the hole moves between the two spins, then everywhere where you had red turns to blue, and where you had blue turns to red. So you can directly see how this parity of the antiferromagnetic ordering has shifted. I can actually show you this even better if I take out this antiferromagnetic ordering, this staggering -1 to the D, this up, down, and I just plot the parity now of the antiferromagnet to the left or to the right of the hole. And here you can see we get one type of parity if the hole is outside of that region, and we get another type of parity for the antiferromagnetic ordering if the hole is between the two spins that we're seeing. So we can directly see this spin flip in the parity, this non-local manifestation of this individual hole that's affecting our entire many-body system. Okay, now that let me maybe stop here for a second. Any questions what the single hole is doing? Because now we're going to take it up and ask what do many holes actually do in the system? And you will see that's actually simple once you understood what a single hole is doing. So now we're going to do the same thing for many holes. So remember, a single hole is like a domain wall for the antiferromagnet. Any questions on this? Everybody fine with that? Okay, then let's try ourselves what happens with many holes. So now I have the same system, I just have many holes. And if you look at this system and with many holes, you actually see, well, actually the same thing happens as for a single hole. Each time there's a hole, the parity of the corresponding antiferromagnet flips in sign by -1. So from +1, we go to -1 parity, we go again back to +1 parity, we cross another hole, we cross another hole, we go back to -1 parity. Each time we cross a hole, the parity of this antiferromagnetic ordering flips, okay? And if you look a little bit closer at this image, you actually see, well, that's interesting, because if I could remove the holes from the system, if I could squeeze out these holes and compress the system together to get rid of the holes, then you see actually you have a nice antiferromagnet, because you have down, up, down, up, down, up, down, up. You have a beautiful antiferromagnet back again that you see in this fictitious space that we call squeezed space, because we remove the holes from the system, and in the squeezed space, we nicely recover the antiferromagnetic ordering of the system again. But we can only see it in the squeeze space. Why? Because imagine I want to know how is this spin correlated with this spin. Well, this will depend on the number of holes we have in between. And if this number of holes is not fixed, but fluctuates from shot to shot, sometimes you have one hole, sometimes you have two holes, sometimes you have three holes. So this will flip the spin over here. And if you correlate those two spins under the fluctuating number of holes in the system, you will get a completely random result. There's another way we can take care of what the holes do is by introducing a so-called non-local correlator, this string correlator, which tries to predict how is this spin ordered relative to this spin. And if we wouldn't know anything, the result would be 0 because we have this fluctuating number of holes. But if we can take into account that if there's a hole that the parity flips by -1, then we can take that into account maybe. And this is what this function here in between does. So in the string correlator, actually this operator in the middle, it just counts how many holes there are in between those two spins and accounts for the -1 phase factors that we get in those two holes. So let me put this into context actually just in the remaining 10 minutes now, how this connects to the phases, order parameters and phases of matter that you might know so far. So far, I think you probably have been taught in your condensed matter or statistical physics courses that we have different order parameters for phases of matter. And in this traditional Landau paradigm of phase transitions, we typically characterize the order parameter by some operator A, which we look at how it correlates at 2 points in space. And if we take the distance between those 2 points in space to infinity, and this correlator assumes a constant value, then we say this is a good order parameter for the phase of matter that we're characterizing. Let me give you a few examples to make this more concrete. So imagine you have a ferromagnet, okay? And then of course, the magnetization of the ferromagnet is the order parameter, because if we have a ferromagnet where all spins are aligned, if you tell me locally what the spin is doing here, in which direction it's pointing, I will be able to take this local knowledge and predict what the spin is going to do anywhere else in the system, okay? Because we know the spins are aligned. So if you know the spin points up here, you know anywhere else on the chain, the spin will also be pointing up. Same for an perfect antiferromagnet. If you know you have this up, down, up, down, up, down ordering, if you tell me this spin is up, I will be able to tell you what the spin 100 sites away is going to be oriented like, if I have this perfect up, down ordering. Or take a BC condensate wave function. You tell me the amplitude and phase of the condensate wave function at 1 point in space, and I can perfectly predict to you what the phase and amplitude of the wave function at some other point in space is going to be like. Same for a BCS superconductor. These are all examples of so-called local order parameters, because the local knowledge of the system allows you to predict what's going to happen anywhere else in the system. That's why we speak of these as local order parameters. Now, what people have learned in the past 20, 30 years is that there's a much more general classification scheme for phases of matter that is not based on this Landau paradigm, but which can be extended by this, for example, in one dimension by these so-called string correlators. Yeah? So there you want to know how these two, how this operator correlates at points x and y. But in order for this to go to a constant value, you actually need to know what's happening in between those 2 points in space to predict what this correlator is going to be. So you not only need to know what's happening on x and y, you need to know what's happening on all the points between x and y also to predict a certain outcome. So this is different from a local order parameter, because now it's not sufficient to know what's happening at x or at y. You need to know what's happening everywhere in the system. So you really need a global microscopic view on your many-body state to be able to evaluate this correlation function. Yes, and our correlator here that I showed you here in this string correlator is a very good example of that, because if you just know the spin points up here, you cannot predict what the spin is going to do over here if you don't know how many holes there were in between. Because remember, each time there's a hole, this parity will be flipped by plus or minus 1, right? So you need to know how many holes were in between. So you need to know not only the local thing that's happening here, but you need the global view of the wave function, and this operator actually takes that into account. So these non-local correlators are very powerful. They really allow us to predict new phenomena in condensed matter physics, new types of orderings which we could not predict it before, which do not fall into this standard Landau classification scheme. So here's now an example. Let me show you that, can say a lot, but let's look at data, what data says to this. So let's look at this one-dimensional chain, and let's put many holes into it, 30%, 50%, 80% number of holes into the chain. And let's look at the spin-spin correlation function. So if there's no hole in between the spins, the distance is 1, so the spins are right next to each other, they will of course align antiferromagnetically. But if they're now, the distance is larger than 1, then you see from the experiment, we're not seeing anything. It gives us a 0 expectation value for the correlation function because we have this fluctuating number of holes, because we cannot predict from this local knowledge of the spin what the other one is going to do. But if I now include my knowledge of the holes, where the holes are in the system, and go back to the string correlator and now include the position of the holes and how they flip the parity of the antiferromagnet, then you see how you beautifully recover the antiferromagnetic ordering in the system, how you can reveal this so-called hidden order parameter now directly in the experiment. So this is very important. You are now able to measure with these quantum simulators hidden order parameters that you simply have no access to in standard condensed matter experiments. Okay, I will jump over the Haldane phase. I'll just keep it in the notes. It's another example of the same kind of physics that occurs. I just want to briefly at the end, just very briefly show you how life is. We talked a lot about 1D. I want to show you actually how life in 2D is very different, and at least give you a flavor of why it's different in 2D. So again, the question we're asking is the same question. We want to understand how does a single hole behave now in a two-dimensional antiferromagnet. And this is actually a very tricky question, very difficult. Actually, just to show you that it is difficult, I found this nice paper from 1989 from Charlie Kane, Patrick Lee, and Nick Reed, some of the 3 greatest condensed matter physicists of our days that actually worked on this kind of Gedanken experiment. Now, why is this different? So let's imagine I have a two-dimensional antiferromagnet, which I sketch here, and I put a hole, or equivalently, what we like to do more in the experiment is put a doubly occupied site. And now again, you have this competition between kinetic and magnetic energy. The doublon, or the hole, actually what they want to do is delocalize, but the spins want to align antiferromagnetically. But now look how this situation is very different from 1D. Let's move the doublon. If we move the doublon, if this spin up hops over here and leaves behind this spin down here, so the doublon is moved, it is delocalized, it has minimized kinetic energy, then it will leave behind a trace of ferromagnetically aligned spins. That's not good because that costs magnetic energy, because remember, you have an antiferromagnetic Heisenberg model. If you move more, let's have this doublon move more, so this spin down hops over here, so the doublon has moved again. Now you have even more flipped spins left behind. So you see in big contrast to 1D, where the hole or the doublon can move arbitrarily far from the spinon, here this is not the case in 2D. The more you move away, the more energy cost in magnetic energy you leave behind. So the further you move, the more this costs you in magnetic energy. So you don't have this phenomena of deconfinement or spin charge fractionalization, but you have something else in 2D. And what you have in 2D is actually a so-called polaron that forms around this impurity. So around this impurity, you have now a bubble of modified spin correlations in the system. And within this modified spin correlations, the impurity can delocalize a bit, so it can minimize the energy a little bit, but not over the entire system. But that would cost too much magnetic energy cost, so it does it only over a finite range of the system. And so what you actually get in this configuration is a so-called magnetic polaron, a distorted spin environment around this single impurity that you see. And I just want to show you some data that we can really measure, take photos now of this single impurity, of this new quasi-particle that emerges in 2D. Here's the doublon, the mobile doublon that we take a photo of, and you can see how in the vicinity of this doublon, the spin correlations are actually distorted relative to the background. This becomes even clearer if you look at, for example, diagonal spin correlations. In the vicinity of the impurity, you have this very, very strongly modified spin correlations. They can even completely change sign, showing you the dramatic modifications that the single dopant now does in the many-body system. All right, I think I'm pretty much at in the end. There's more to say, but I want to leave some questions open also for some time also for questions. So, but let me, before I leave you with that, I want to give credit to the people who did the experiments in the lab. So let me quickly go here again. So, yes, so on the Fermi experiment that I talked about a lot, that was Jaya's PhD thesis was the spin charge separation I talked about. Yanis did the polaron experiments, and Dominic and Sarah are the new PhD students. Mim and Guillaume were postdocs in the experiment, and Christian Ghosh led that team. On the rubidium experiment, the bosonic quantum gas microscope, the team was also led by Christian Ghosh, and Tony, Simon, and David are the PhD students, and June was the postdoc who now left for a position in Shanghai. And yeah, with that, thanks a lot for listening. I hope you found it interesting and you got a little bit of the physics that we can study in these optical lattices, in these quantum simulators, you know, working our way up from simple problems, single particle problems, to some of the most complex things we are actually doing now in the lab. I just wanted to give you a little bit of the flavor, and maybe now you're motivated to read more on this and learn more about these phenomena. Thanks a lot for your attention.
Thank you very much. Questions and comments?
Hello, sir. I have a question. So this one dimension, when we are shifting from one dimension to two dimension chain, so suddenly that delocalized hole becomes a localized. I mean, because the magnetic energy should be minimized. So just changing the dimension, why this is happening?
Sorry, why? The last question, please. Just the last sentence.
So just changing the dimension, just from one dimension to two dimension, I mean, why that delocalized hole becomes a localized? I mean,
yes, well, that's the fundamental change. What happens when you go from 1D to 2D? That's really dramatically different physics. So you think it should be similar, but indeed it's completely different physics. And of course you try to, because in the 1D case, you know, the hole can move away from the spinon and there's no energy cost for it to do that. So the more the hole moves, it can separate from the spinon as far as it wants. It doesn't cost more energy to do that. But in 2D already, this is different. This is dramatically different. The more the hole moves, the more magnetic energy cost it leaves behind, as you correctly say. So the physics is entirely different in 1D and 2D for the two situations. If you ask me why, well, that's why, right? I mean, that's but it is striking that there's such a huge difference of these two phenomena.
yes.
There is one more question.
Yes.
Minal Kantigiri, do you like to ask yourself directly? Then unmute and ask. Okay, then I can read. The single particle motion and hole motion is same, but in presence of magnetic field, particle motions and hole motion will remain same.
Yes, so that's of course correct. And we will have effectively, well, remember for us, we're dealing with neutral atoms. So there's no Lorentz force on our neutral atoms, right? They are not charged. So that's a huge difference from electrons. But if we would do this with electrons and remove an electron and create an effectively positively charged hole, it would of course move in the opposite direction. You would have different type of physics. That's completely correct. So we can mimic the behavior of magnetic fields, the Lorentz force, by some tricks, by engineering our lattices to carry some phase shifts when you hop from one side to the next. So basically what you're trying to mimic with that is the Aronoff-Bohm phase shift that you pick up for a charged particle in a real magnetic field. You try to mimic by having kind of a laser-induced hopping with phase factors on our lattices. Yes, indeed, by this laser-assisted hopping. That's precisely correct.
So there is one more question. Is there any speed limit for the ballistic propagation in 1D, or can it be arbitrarily large?
Yes, very good question. So Indeed, it cannot be arbitrarily large, it's bounded, and you already know the answer to what the maximum velocity is. So what do you think? Actually, what is, if I give you let me ask like this, if I give you a dispersion relation, how do you calculate the velocity of the wave packet? If I give you a certain dispersion relation, so the connection between energy and momentum, how do you calculate from this dispersion relation the wave packet, the velocity? Anybody know? Taking the derivative, exactly the omega decay. And now if you do this for the band, for the single band that I showed you, the dispersion relation is not parabolic like for particle in free space, but it's cosinusoidal. Okay, so for a free particle, you know, E is proportional to k squared, to p squared. But in a lattice, actually, we have E is proportional to cosine Ka. Okay, and there's a maximum velocity. If you take the derivative, you will see there's a maximum velocity exactly in the middle of the band for a Bloch wave vector of pi over 2a. And that basically, that maximum velocity is tunneling matrix elements times lattice constant divided by h bar. TA divided by h bar. So it's proportional to the tunneling matrix element, as we saw, as we intuitively also would have guessed. You know, the higher the tunneling matrix, the faster the particle moves. So there's indeed an upper limit, and the maximum velocity is this just, I think, 2TA divided by h bar. I have to do the calculation, but this is how you would do it.
There is one question from Noah Van Horn. So Noah, can you ask yourself directly?
Yes, sure.
You can unmute and ask.
Yes, so the question is, you showed that from the Hubbard model, you could then produce a Heisenberg exchange interaction. And then we went on to see many really fantastic things that you could reproduce in the atoms and optical lattices with that interaction, ferromagnetic or antiferromagnetic and so on. So I was wondering if you think other types of interactions could also be reproduced, such as the Jeller-Simski-Maria interaction, which instead of producing ferromagnetic or antiferromagnetic alignment, produces a, I guess, perpendicular alignment. So the energy is minimized for the cross product, and then tends to create spirals of this.
Yes. Yeah, this one might be a bit more tricky, although maybe with some spin-orbit interaction, you can realize something like that also. What is more natural for us to do is actually change the anisotropy of the spin model. So we can quite naturally, by using fresh path resonances, go away from the Heisenberg point to different XXZ models. You know, so that's quite natural for us to do actually in the experiment. With the Maria interaction, I don't know exactly. I think there might be some possibilities with spin orbit coupling, but I would have to look. I have to see again. There might have been proposals for that, but we didn't do that in the experiment.
Any other question? I don't see any more question in the chat box. So I have a general question. This spin charge separation in 1D, does it happen only in the limit of tight binding approximation and strong interaction limit?
I don't think tight binding is so crucial for it, but it's certainly something that only occurs in the strong interaction limit. Yes, so that's true. But I don't think tight binding is absolutely necessary for it. Yes.
So if there is no more question, let us thank very excellent and pedagogical, and I am sure many students have learned many new things, and students have acquired some knowledge about the state-of-the-art experimental physics. from one of the leading experimentalists of the world. So with this, I thank you, all of you, for attending this lecture, and especially many thanks to Professor Bloch for giving this talk and for your time. Thank you very much.
And I will send you the slides so you can have a look at the slides. There's a bit more information also in the slides. Okay? Thanks, everybody. Have a nice day. Bye.